Okay, folks, let, let's get going. So yesterday we started working our way through a weak acid, weak base titration, and we were tracking what the pH should theoretically be at different points in that titration. Um, where we left it, we had just reached what we called the equivalence point. Any idea why we called this the equivalence point? Because we have equivalent, easy for me to say, equivalent numbers of moles of acid and moles of base. And we saw that the pH had been slowly rising, and then all of a sudden, that last 5 milliliters to get to the equivalence point made the pH jump up. So now we're going to check, all right, what happens when we add 5 more milliliters of base? So we go just past the equivalence point. So if I start with 50 milliliters of 0.2 molar HF and 55 milliliters of 0.2 molar NaOH. So remind me, what is the reaction that's going to occur when I mix these two things? Okay, it's the reverse of the KB reaction for F minus. So what does that look like? So the student comment was, oh, we use a back and forth arrow, but not really, because we decided, yeah, we're sending this reaction to completion. Why did we say we're sending it to completion? Because the Ka value is very high. Or not the Ka value, but the K value for this reaction is very high. And the other thing we did differently yesterday, what did we put into our rice chart instead of concentration? Millimoles. Again, when you're mixing two solutions, what matters is how many moles of each, because you're using different volumes. So to combine them, you really need to put it in moles. And we did millimoles just for convenience. So 50 milliliters of 0.2 molar HF is going to be 10 millimoles, which it has been for all the other calculations. 55 milliliters of 0.2 molar NaOH is how many millimoles? 11. So what has changed now from my earlier? Now HF is limiting. So what's the change going to be? Minus 10. Minus 10, and then plus 10 of these. All right. So I end up with 0 HF, 1 millimole of OH minus, 10 millimoles of F minus. So now what I have is a mixture of OH minus and F minus. How am I going to find the pH? Oh, I know how much OH minus there is. So I can find the concentration of OH minus, find the pOH, and then find the pH. So concentration of OH minus is 1 millimole divided by 105 milliliters. So, I don't know, 0.009 something, 0.0095. So my pOH is the negative log of that. It's going to be very close to 2. 2.02. And then pH is 14 minus that. 11.98. So again, let's look at our big picture here. We were adding NaOH, the pH rose slowly. Went from 4.1 to 8.07 now to 11.98. So over the first 45 milliliters we added, the pH essentially changed by about 2 units. And then over the next 10 milliliters, it changed by 8 units. This is going to be a feature of every titration. When you reach the equivalence point, there is a big jump in the pH value. So then we might ask, okay, what happens after that? So the last calculation we're asked to do, you can go fill this in while I do it. Okay, so we do the same calculation. We find now the pH has risen to 12.6. So it started to level off again. Any idea why it's leveling off at this point? What's the pH of the titrant solution, the solution that we're adding? So the pH of the pure titrant solution, the pure NaOH, so the pOH is going to be negative log of 0.2, which is 0.7, so the pH is 13.3. So if we add an infinite amount of titrant solution, what's the highest the pH is going to get? 13.3. So it makes sense that the graph should level off as it approaches 13.3. So here we got to 12.6. Let's make a rough sketch of what this looks like. So if we make a graph of pH versus volume of NaOH added, we know that at 0, the pH was 2. Let me see if I can mark this off roughly evenly. 2, 4, 6, 8, 10, 12, 14. How'd I do? All right. And then this axis, I want to go up to 75. So maybe if I say 100 is going to be over here. No, I don't want to go up to 100. This is 75. And 50 and 25 over there. So I started at a pH of about 2 when 0 had been added. 5 milliliters, it was just slightly above 2. At 25 milliliters, it was a little above 3. At 45 milliliters, it was at 4.1. At 50 milliliters, it was right about 8. 55 milliliters, it was up to about 12. And then 75 milliliters, it was a little above 12. If I smooth that out, what would it look like? It looks kind of like this. Rising slowly, 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 jump. And then leveling off. I missed my last point, but you get the picture. This is what we call a titration curve. So a titration curve plots pH versus volume of titrant added. And they generally have this shape. And we just did all the math to show why they have this shape. All right. So let's just say if I give you a titration curve, what are some features you're going to want to recognize? One is what we call the buffering region. In the buffering region, this is where we had a mixture of what two things? If we go back, the buffering region would have been these first few points. We had a mixture of HF and F minus. We had a mixture of acid and conjugate base. So in that buffering region, you've got a mixture of acid and conjugate base. And that's what we call a buffer. So when you add more base to the buffer, does the pH change by a lot? No, because the buffer is doing its job. So that's why the graph is relatively flat. Then we reach the middle of the graph. Middle of the graph we call the equivalence point. And what's special about the equivalence point? All right, the number of moles of acid and moles of base are equal. So this is the point that's going to help us find the concentration of our unknown. Because when we say moles of acid equals moles of base, remember one way to find moles is moles per liter moles of acid per liter times liters. It's going to equal the moles of base per liter times the liters of base. Another way this is often written is MAVA equals MB VB. Molarity of acid times volume of acid equals molarity of base times volume of base. And that'll be true at the equivalence point. In the buffering region, we had said we had a mixture of HA and A minus. When we reach the equivalence point, really that's not what we have anymore. What do we have in the solution when we reach the equivalence point? If we go back to our calculation at the equivalence point, which was here. Do we have any of our weak acid left? No, it's all been used up. So all we have in the solution is the weak base, A minus, the conjugate base. So at this point in the solution, basically all HA has been converted to A minus. And when I say all, remember at equilibrium we can't really have a zero. So there is still a tiny percentage that's HA. So I guess I could say almost all. But the amount of HA that's left is pretty much negligible. When we get beyond the equivalence point, really what's determining the pH? The extra base that I've added. So from that point on, all this part of the graph, this is excess OH minus. Yeah. So the student question is, why are we calling this the equivalence point if there's no acid left? So when we say equivalence, this is why I stated it the way I did, equivalent numbers of moles of acid and base have been added. Now when you've added a weak acid and a strong base, what happens is all of the acid has been converted to its conjugate base. But the equivalency is about the number of moles of acid added and the number of moles of base added. So it's not talking about the moles of acid and base present in the solution. So we already answered this question by doing the math. we say the equivalence point is in the middle of that vertical jump in the pH. So why is that? What was keeping the pH from jumping up? The buffer. It was buffering. We've reached the point where we broke our buffer. So this is the point where we've overcome the buffering capacity. Extra base at that point just makes the pH jump. So you should be able to look at any titration curve, spot the equivalence point, just by looking for that vertical jump. And then we use the equivalence point to determine the concentration of our unknown. So the questions come up in a couple of classes. How do you know what indicator you should use for a given titration? Well, if you want to know what indicator to use in a given titration, it's helpful to be able to answer the question, what will the pH be at the equivalence point? And it's going to depend on your type of titration. So if you have you can imagine 3 types of titration. Strong acid and strong base. If you have a strong acid and a strong base, when you add equal numbers of moles of them, what does your instinct tell you the pH will be at equilibrium? 7. Why? It's a neutralization reaction, and it's a fair fight. It's equal. They're both strong. They cancel each other out. So the pH of the equivalence point would be 7. We did the calculations for an example where we had a weak acid and a strong base. And the pH of the equivalence point was 8.07. In general, if you have a weak acid and a strong base, who's going to win the fight if there's equal numbers of them? The base. So here the pH will be greater than 7. How much greater than 7 is going to depend really on what is the strength of the weak acid. And if you have a strong acid but a weak base, who will win? The acid will win, so the pH will be less than 7. All right, student question, which I anticipated. Would you ever have a weak acid and a weak base? And the answer is probably not, because our titration is predicated on the idea that the reaction between the two goes to completion. And so to ensure that that happens, you want to make sure that you have one component be strong. So why would it be helpful to know the pH of the equivalence point? You can use this to choose an appropriate indicator for a given titration. So if we had chosen for our titration, our hypothetical titration here that we graphed out, what if we had chosen an indicator that changed color at a pH of 4? It wouldn't really show us anything because pH 4 is, right about here on our graph. So the color would have changed too early. It wouldn't tell us where the equivalence point is. So that would be a bad choice. Better to choose something that's going to change color, somewhere a little above 7. The question is there an indicator for every pH, more or less? And the answer is, yeah. I can show you, most of you don't have the textbook, but there's a whole page in the textbook that shows you indicators that change color in each range, and it pretty much covers the whole range of pH. All right, now the third thing you can get out of a titration curve is what we call the half equivalence point. And that would be when the volume of NaOH added is half of the volume that it took to get to the equivalence point. So if my equivalence point is here, and this took a volume of X, then the half equivalence point would be when the volume added was X over 2. Let's go back to our hypothetical titration. When did we reach the half equivalence point in this titration? Well, the equivalence point was when we had added 50 milliliters of base. So if I go back to 25 milliliters, what's special about this point in the titration? Well, someone said 3.14. Yeah, that was just a coincidence. But in general, what did we notice was true here? At the half equivalence point, we've converted half of our acid into conjugate base. So the concentrations of acid and conjugate base are equal. And we said whenever that is true, what else will be true? pH equals pKa. So at this point, half of HA is converted to A minus. So the concentration of HA equals the concentration of A minus. And when that is true, the pH equals the pKa. So in analyzing a titration curve, if you find the half equivalence point, it will tell you the pKa of the acid you're analyzing. So this is a good, reliable way to measure pKa's. Yep. Question. So the student question is, when would you ever use this way? So you're saying because I gave you a list of Ka values? So the question is, if you have the equivalence point, why would you care about the half? The half equivalence point gives you a different piece of information. The equivalence point, at the equivalence point, you can use this equation, MAVA equals MVB, to find the unknown concentration, right? One of these concentrations is unknown, and you solve for it. So if your goal of the titration is to find the concentration of the unknown, the equivalence point is the point that's important. Sometimes you might have an acid that you don't know the Ka of it. So by doing a titration like this, you can find its Ka, right? By doing a titration and then using the half equivalence point, that's where you can find the pKa, which will lead you to the Ka. So it's an experimental technique for finding Ka. I gave you a list of Ka values. How do you think we know those Ka values? Because people have done titrations and found the Ka values for those different acids. All right, so summary. Really, terminology-wise, you should know what this flat part at the beginning we call the buffering region. But more importantly, you want to know this is the equivalence point. It's used to find unknown concentration. And as much as I hate to give you a formula because you're going to memorize the formula and not think about it, I am going to write it down. That's the point where molarity of acid added times volume of acid added equals the molarity of base added times the volume of base added. And then the half equivalence point is where pH equals pKa. So next week we'll do a bunch of titrations. So you'll have a bunch of titration curves that you're going to analyze to find experimentally pKa's of some acids. You can then compare to the accepted values. All right. We did an example of a weak acid with a strong base. Of course, you can do titrations the other way around. Everything we said would be reversed. If you start with a weak base, the pH would be high. You add HCl, the pH is going to drop slowly until you reach the equivalence point. So this is still called the equivalence point, and it's still the same equation that applies. But there is a slight difference. If I go to the half equivalence point, for a base, I wouldn't be talking about Ka, I'd be talking about Kb. So at the half equivalence point, we would say POH equals the pKb. Or another way to say that is the pH equals the pKa of the conjugate acid. But conceptually, it's the exact same thing. You start out with base. You're adding strong acid. That's converting it to its conjugate acid. At the half equivalence point, you have equal concentrations of base and conjugate acid. So then last thing, what do you think would happen if I have a polyprotic acid? Be like a double curve. All right, what does that mean? All right, you would actually see multiple equivalence points and multiple jumps. So let's say we start out with H2A. At the beginning, we have mostly H2A. As we add strong base, what's the first thing that happens? It becomes HA minus. We pull off the first proton. So you would start and you would see a buffering region where you're pulling off the first proton, right? This first part of the curve would be where H2A is being converted to HA minus. Now at some point, you're going to run out of H2A. That'll be your first equivalence point, and you're going to see a jump in pH there. But instead of jumping all the way up, that extra OH minus you add now doesn't just float freely in solution. What does it start doing? Starts taking away the second proton. So we see another buffering region. And I want to get the lengths about the same. So this would be where HA minus is being converted to A2 minus. And if the volume it takes to get to the first equivalence point is X, it's going to take 2X to get to the second equivalence point. So did I do this about right? Is this about 2X here? I hope so. So when we reach 2X, we're going to see another jump and then a leveling off. So we have multiple equivalence points. That also means we have multiple half equivalence points. At the first half equivalence point, so this would be at X over 2. What would we say about the pH at that point? pKa1. And then second half equivalence point is going to be at a volume of what? 3x over 2. And at that point, the pH will equal pKa2. So for polyprotic acid, you have multiple Ka values. So it can buffer at different pHs. So the question is, what about H3PO4? Would it have 3 steps? In theory, H3PO4 would have 3 steps. The issue is the third Ka value. If you have your Ka sheet in front of you, if you look at the third Ka value for H3PO4, it's 4.8 times 10 to the negative 13th. So that means you wouldn't even hit the, it would buffer around a pH of 12 point something. Really high already. So you probably would never see the third jump because you're not going to be adding base that's that concentrated to get the pH up above that. But for citric acid, for example, you could see 3 bumps in the titration curve. That's a triprotic acid. And the third pKa is still only around 6. So the question is there a polyprotic acid where the first two pKa's are very similar? Yeah, I mean, for citric acid, they're not that far apart. So you may, if you're doing polyprotic acid with similar Ka values for the first couple, these steps might be really hard to distinguish because they'd be small. What other questions do you have? All right, let's quickly take a look at the objectives then. Make sure we've hit them. Learning objective 6.12. The student can reason about the distinction between strong and weak acid solutions with similar values of pH, including the percent ionization of the acids, the concentrations needed to achieve the same pH, and the amount of base needed to reach the equivalence point of a titration. Wow. Yeah, let's unpack it. All right. Distinction between strong and weak acid solutions with similar values of pH. So a strong acid, a solution of HCl at a pH of 2 and a solution of acetic acid at a pH of 2. To have the same pH, which requires a higher concentration? Acetic acid, why? All right. This requires higher concentration. To reach the same pH. It will have a lower percent ionization. So the percent ionization piece is 100% for the strong. Less than 100% for the weak. Concentrations needed to achieve the same pH. We already mentioned that. And the amount of base needed to reach the equivalence point in a titration. Well, we said the weak acid has to have higher concentration. So what does that mean about how much base we would have to add to reach the equivalence point? More base is needed. So this last piece since the weak acid must be more concentrated, more base would be needed to reach the equivalence point. So there's a lot of words there. Are there questions now about what this objective implies? Okay. 6.13, the student can interpret titration data for monoprotic or polyprotic acids involving titration of a weak or a strong acid by strong base, or a weak or strong base by strong acid, to determine the concentration of titrant and the pKa for the weak acid or the pKa for the weak base. All right. To determine the concentration, where do we go? The equivalence point. And to determine the pKa, where do we go? To the half equivalence point. pH equals pKa, or POH equals pKb. So that was the point of today. All right. Student can, given an arbitrary mixture of a weak and strong acids and bases, including polyprotic systems, determine which species will react strongly with one another, i.e. with K greater than 1, and what species will be present in large concentrations at equilibrium. So this is what the entire first half of the problem set is about. It's, if I mix this acid and this base, which reaction is going to go to completion, and then sending that reaction to completion. So these are really the calculations we were practicing when we went through the titration, or when we talked about adding acid or base to the buffer solution. It's deciding what reacts with what, sending the reaction to completion, and then determining what's left in solution. That's what this objective is all about. So you'll practice it on the problem set. We practiced it a bunch today. All right, 6.18, student can design a buffer solution with a target pH and buffer capacity by selecting an appropriate conjugate acid base pair and estimating the concentrations needed to achieve the desired capacity. You'll do that on the problem. We talked about buffers in general. We haven't actually done this yet, but there's a question on the problem set that asks you to do this one. And then lastly, the student can identify a solution as being a buffer solution and explain the buffer mechanism in terms of the reactions that occur with the addition of acid or base. How do you identify a buffer solution? What do you look for? A weak acid-base conjugate pair. And you need both present in significant amounts. In other words, one of them can't be near zero. There you have it. I'm done lecturing for the year.